Welcome to this debrief of the 3 Section B questions in the March 26 PM mock exam. As with Section A, I recommend that you have a go at Section B yourself before watching the debrief. If the exam has been removed from the platform, then what you can do is pause each question as I get to it and attempt it just reading it from the screen. As we see here, there are 30 marks available for Section B, which is about 54 minutes we would allocate to the whole of Section B. But as it's in 3 case studies, I recommend thinking along the lines of 18 minutes per case study. That's per set of 5 questions. Because in each case study, some will be a bit easier, some will be a bit harder. So if we allocate 18 minutes to each, that means we've got a good time management strategy. And as is typical for a Section B question, we have the information relating to the question on the left, and then we've got, here's question 16, but 17, 18, 19 and 20 will all use this information on Frutico. I'm not going to read through this on the video, so please pause the video, read through this, and I'll scroll down so you can read the next bit. So as we can see, this is a limiting factor question, specifically using linear programming, which is where we have more than one constraint. You'll never have to draw a linear programming graph such as this, but you could be asked to label and to read off it and interpret it. And we can see that the non-negativity constraints, so both K and M, which is defined by the 2-axis, anything to the right is where K is greater than 0, anything above the horizontals where M is greater than 0. C1 for apples is plotted here. C2 for machines is plotted here, C3 for labour is plotted here, and C4 you see is this vertical line here. We don't often see minimum orders, and so what that has done is defined our feasible region as per where I'm moving my mouse now. So this part of C4, this part of C2, this part of C1, and this part of the x-axis. So don't let that put you off. It's exactly the same as we'd normally do, just our feasible region is shifted across because of this minimum order. And this is the ISO contribution line, and hopefully you'll remember we move this up parallel, and the optimum point is the last one it will hit within any intersection in this feasible region. So question 16, if apple supply was in shortage this month, what is the contribution per limiting factor for product key to the nearest whole dollar? So looking at key, our selling price is 58 and our variable costs are 54. Which means our contribution is 4. And in terms of limiting factors, it uses $20 of apples at 10 per kilogram. So that's 2 kilograms. So the contribution per limiting factor is 4/2. Next, we need to calculate the maximum profit to be earned for next month at point C. And it's telling us that's the optimal production plan to the nearest whole dollar. Point C is here on the graph where my arrow is. And you see it's the intersection of the lines C1 and C2. C1 being this one here and C2 being this one here. Because it's an intersection, the value of K is the same for both lines and the value of M is the same for both lines. And although we can't read it off the graph, we can see that the value of K is somewhere around 7.5 and the value of M is probably 6.5 or thereabouts. Remember, we're working in thousands, but we can use that as a sense check as we do our calculation. And the way we do this is we use simultaneous equations. We take the equation for C1 and C2. At the moment they're given as inequalities, but we turn them into normal equations. You see I've written them out here. You wouldn't need to do that if you wanted to save a bit of time, but they've turned from inequalities here into equations. And that's because we want to find the point on the line, and the equals refers to what's happening exactly on the line. The less than or equal to refers to what's happening below and to the left. There are 2 main ways to do simultaneous equations. One is where you make one of the terms the same. Either you have the same number of K's or the same number of M's. You subtract one from the other and then solve and then take that solution and plug back into one of the original equations. Or use the approach which I'm going to do now where you substitute. And so I'm just going to rearrange this one to make K on its own this side. Depending on how confident you are with simultaneous equations, don't write stuff out here just for the sake of it. The scratch pad is for your use. The examiner won't look at it. So now I'm going to plug C2 into C1, and every time I see a K, I'm just going to substitute with this bit. So I've rewritten C1 out, but instead of K, I've now put this bit in place. So I'm going to expand the brackets next. And I just spotted I have made an error there. It should have been 25,000. I know that because I shouldn't end up with a negative. If I just go back to what I had, I saw that I had a negative amounts of M's. And if I move the M's across this side and this across to this side, I'd have had a negative. And that made me think I'd probably made a mistake. And I had put 2,500 instead of 25,000. So 5,000, I bring the 24 across, so I end up with 26,000. That equals 4M. So 6,500 equals M. I think that's what I guesstimated from looking at the axis here. So I'm going to put that value of M into C2. We end up with K equals 8,750. And I think I guessed it was about 8 earlier, just reading off the graph. So that sense check has helped me reassure myself that my values are certainly in the ballpark. So I now know how many M's and how many K's are in the optimum production plan. And so we now use the ISO contribution line because we get a contribution of 4 for every K we make, a contribution of 6 for every M we make. So we get 4 for every K and there's 8,750 of those, 6 for every M and there's 6,500 of those. So that's 74,000 contribution. Be very careful because we do have some fixed costs and we're looking for profit, not contribution. So the answer is 67,000. Next, based on the optimum production plan, which two of the following will have a shadow price that is 0. So we've got our 4 constraints, C1 to C4. The optimum production plan is where C1 and C2 cross, which means they will have a shadow price, because if we could get more apples or more machine time, then we would improve our contribution. Whereas because labour and minimum order are not at the intersection, if we got more labour or changed the minimum order, that's not going to affect our optimum production. So therefore there's no shadow price for those. So the answer is labour and minimum order. Which of the following is all true about linear programming? Firstly, the shadow price is the maximum total cost a company should pay for one more unit of a scarce resource. That's not correct. It's not the total cost, it's the premium over and above what they would normally pay. And that's because it represents the additional contribution they would get from acquiring one more unit of the scarce resource. So 1 isn't true. Slack occurs when less than the maximum available of a resource is required. That's true. That's exactly what slack is. So the answer is 2 only. Which of the following best describes the feasible region of A, B, C, D? Our options, it shows all feasible production plans that meets all of the constraints with the possibilities of more than one optimum production plan. The first bit's true, but there's not more than one optimum production plan. Second option shows all feasible production plans that meets all of the constraints with only one optimum production plan. That's correct. But we'll just check the others off. It shows all feasible production plans that leave no slack on all 3 resources. So the feasible region is A, B, C, D and everything that's inside. The only points where we can say there is no slack is at an intersection, and there is no slack between those lines that intersect. So where my arrow is here at point B, there's no slack on the minimum order or on machine, but there is slack on apple and labour. So wherever we choose a point, we will always have some slack. It just is different depending on where we choose. So that rules that one out. And it shows all feasible production plans with slack on apple and labour. Well, that's not true because anywhere along this line, or this part of this line, which is part of C1, there's no slack on apples. However, had it just said labour, labour is outside, so there's always slack on labour within the feasible region. So because of the word apple there, that one is not true. Okay, on to question 21, the second case study. Once again, pause the video, have a read through the question, and then we'll make a start on going through these. So we're asked for a market share variance. I always recommend to my students to look at all 5 questions before reading the narrative. I think it helps with time management, and also when you're reading this, it makes more sense. If you choose not to do that, that's your call. But what I would say is if you see a market share variance, just check to see if there is also a market size variance. Similarly, if you see a mixed variance, see if there's a yield variance, and we can see there is both market size and market share. If we've got market size and market share, we can use the same template for both. So a market size variance compares an original figure with some sort of revised figure, and a market share compares the revised with the actual. I definitely recommend learning some templates, and templates for variances are really helpful because we see there's a lot of information here. The risk is we try and use the information to get to the answer. Whereas if you're able to use that template, you use the template to go and find the correct information, you're more likely to get it right and more likely to ignore the distractors that are put in here that are not relevant to the question we're being asked. So we need the original, the revised and the actual. That's our first figures to go looking for. Well, the original is the sales volume that we budgeted for. So that's 240,000. The actual we're given here as 200,000. The revised we aren't given, and we need to use the market size to help calculate that. The original market size was expected to be 1.5 million, turned out to be 1.95. So it was 450,000 higher, which is a 30% increase. And our original market share was 240, so 30% increase is 1.3 multiplied by the 240 gives us 312,000. So once we've got our original, revised and actual, we need to find the difference between each pairing. So there's a 72,000 difference here and 112,000 there. Some people like to use positives and negatives. I prefer not to. It's up to you which way you do it. If you do like I do, I work out my variance and then I look back and work out, is it adverse or favourable? I think I'm less likely to make a mistake. So we now know our variance in units, but we need our variance in dollars. Because they are using marginal costing, we're going to work in contribution. And we always use our budgeted contribution per unit, not our actual, which is the 650 minus the 340. So that's 310. So I've got my market share variance of 34.72 million, my market size at 22.32. I haven't worked out whether it's adverse or favourable, but given the numbers on offer, I can see that it is going to be adverse, but let's just check. Our revised was 312,000. Our actuals was 200, so much lower. And because we're talking about sales, if we sell less, that's an adverse variance. Whereas our original was 240, we revised it up, so if we expected to sell more, then that should have been more sales, so that's a favourable variance. So that's question 21. As you can see, it took a little bit longer, but now onto the market size. I've already done that one, so I quickly make up that time. And that's what I mean when I say using 18 minutes for the whole of each section B question. I'm very comfortable doing that because I know if I invest a bit more time in that first one, I've now quickly answered the second one. Question 23 is the sales price variance. So for the sales price, we look at the budgeted versus the actual selling price, which is the 600 and the 650. And we multiply by the actual volume, which is 200. So that's 10 million, which obviously is one of our options here. Our actual selling price was lower than our budgeted, so that makes it adverse. So which of the following commentary best describes the sales performance of the company in the past year? So the first two mention the aggressive strategy, and it says here they've adopted an aggressive strategy such as aggressive promotion campaign, competitive pricing strategy in an attempt to broaden their market presence in Geeland. Has that aggressive strategy proven to be effective? Well, even without doing the calculation, we can see that the market size has increased, but their volumes have decreased. So in a growing market, they've done less well, despite dropping their price. So we can't choose the top one. So out of the top two, it's most likely to be the second one, that it's not as effective as planned. But let's just check the others because we need to choose the one that best describes performance. The sales volume performance was mainly attributable to factors beyond the control of the sales and marketing team. What that's getting at is the market size. Had the market size gone down and the sales volume gone down accordingly, then we could say that's true. But because the market size has gone up, but their market share has gone down, that is within their control, so we can't choose that one. The sales volume performance has outperformed as compared to budget in all aspects. Well, again, we can see that's not true, so we're going to select the second option. Which two of the following variances are most likely to reflect the responsibility area of the sales and marketing team of the company? Well, we can eliminate market size because that's not controllable by the company. Market share, hopefully you'll see that is the one that is controllable by the sales and marketing team. This one's a little bit trickier. Sales volume can be influenced by the sales and marketing team. If they do well, then they'll influence sales volume. However, one of the things that's completely in their control is price. They set the price they sell at. The price should lead on to a volume change. If they decrease price, you'd expect a higher volume and vice versa, but price is more likely to be their responsibility than sales volume. Okay, and on to the third section B question. Once again, pause the video, read through this, and then I'll scroll down to capture the next bit. So hopefully you've read through that. There's a lot of information there. We can sort of see that there's a learning curve part going to be coming up, and obviously some target costing. We can see the first part of the question is, what is the cost gap? Cost gap is the target cost minus the actual cost. So let's calculate our target cost. The target selling price is 200 and the markup is 35%. That means that markup is included in the target selling price. So we need to multiply by 100 over 135. So that's 148.15. Our actual cost is 160. That's 11.85. Now we need to calculate the new direct material cost based on this additional information. And the way this information is given to us, what we're likely to need to do is take the direct materials now, separate it out based on the percentages here, do some adjustments and then put it back together. And it tells us that 3 of the parts account for 20%, which means the rest must account for 80%, and they cannot be replaced, although an alternative supplier charging 10% has been sourced. So we need to take our $40 and split it into an 80-20 split, and then we do some adjustments on the 20% and some adjustments on the 80. Okay, so I've split into my 80-20 split. I'm going to work on the 20% first. So 20% of the estimated materials cannot be replaced, but we can get a supply for 10% less. So 8 times 90% or 0.9 gives us 720. And then the remainder, so the 80% is in the first couple of sentences. These can be replaced with standard parts, which cost 55% less. If they cost 55% less, that means they cost 45% of what they cost now. So that's 1440. Add on the 720 and I end up with 2160. Now we need to calculate the labour cost for the 100th unit. This uses the information down here and is a learning curve calculation. You are given the information for learning curve in the formula sheet. Y equals AX to the B. Remember, Y is an average. A is the time for the first unit. X is the number of units we're looking at in this part of the calculation. LR is the learning rate, which we're told here is 90%. And B is the index of learning. And if we're given the index of learning, then it makes the calculation a little bit quicker, and it's given to us here. And so what it's telling us is the very first unit will take 45 minutes, and then over time they'll get quicker and quicker and quicker, but when they get to the 100th unit, that improvement in speed will stop. And that's why we're asked to calculate the labour cost for the 100th unit. Now I think it's worth just trying to get a bit of a sense check before we go ahead. If it's $30 an hour, and it takes 45 minutes of labour for the first unit, that means the first unit in terms of labour costs $22.50. All of these are lower, so they could all be true. However, these top two are quite close, particularly that top one there, to that first unit cost. So I'd be very surprised if the top one was correct. I'd still be surprised if the second one was correct. So if you're running out of time and haven't got time to do a learning curve calculation, a quick side calculation like that would then, in my view, narrow it down to one of these bottom two, at which point it is a bit of a guess, but at least we've now got a 50-50 guess rather than a 25% chance of getting it right. Let's do the calculation properly. So in order to find the cost of the 100th unit, we need to find the time taken for the 100th unit and then multiply that by the hourly rate. And the way we find the time for the 100th unit, we calculate first the time for the first 100 units, and then separately we calculate the time for the first 99 units, and the difference between those two is the time for the 100th. So if we take Y equals AX to the B, A is 45 minutes. You have to choose whether to convert it into hours or to stick with minutes. At some point we'll have to do the conversion. Let's stick with minutes. So our value of A is 45. X, we're looking at now the average time for the first 100 units. And the value of B is given to us. You should never have a positive value of B. But before we go ahead, and this is why we should always practice on the practice platform, the calculator they give us doesn't do these calculations very well. So you see I've done 100 to the power of minus 0.152, but we get an error. It doesn't allow us to do the calculation that way. So what we need to do is understand how we do a workaround. And the way we do it, and it's a pain that we have to do this, is we do 100 to the power of 0.152 positive, and that gives us the answer. And then we need to find the reciprocal, so 1 over that. So then we press the x to the minus 1, enter. So now I've got the calculation for 100 to the power of minus 1.52, and then I multiply by 45. This has given me the average time per unit for the first 100 units. I need the time for the full 100 units. So I multiply the average by 100, that's the total time. So here we've got 2,234 minutes. I've kept a few decimal places, and we should do that for these learning curve calculations. It's less of a problem when we've got a selection here, but we don't want to incorporate a rounding error. So now we do the same again, but this time we're doing it with 99. So we do 99 to the power of 0.152. Then we do the reciprocal. Then we multiply by 45 to give us the average time per unit for the first 99 units. And then we multiply that by 99 to give us a total time for the first 99. So now we can work out the difference in minutes. This is the time for 99. So I'm going to subtract the time for 100. So there's an 18.96 minute difference. You will now see that that is one of our distractors. But remember, this is in minutes. We now need to convert it to hours. So we divide by 60, and we are paying 30 per hour. Gives us 9.48. And that's the bottom answer there. You remember at the start I said these top two felt a bit close to the time for the first unit, and I wouldn't be surprised if this third distractor also is if you've done a small error somewhere in the calculation. Okay, question 29, which of the following statements is true? We're given some additional information here. The new direct labour cost per unit has been based on an expected learning rate of 90%, but now the finance director realised a 92% learning rate should be applied. It will still end after the 100th unit. So this is what's the difference between a 90% and a 92%. A lower percentage is a faster learning rate. Intuitively, that doesn't feel right, but you remember what we're doing is we are looking at the average time. Each time we double the number of units or double the number of batches, and that average time is going down. And with a 90% learning rate, once we double, it's 90% of the previous average. With a 92%, when we double, it's 92% of the previous average, which therefore means it's a slower learning rate. And this is quite a complicated question because we need to work out what that's going to do in terms of our speed of learning, what that's going to do in terms of our labour cost, and what that's going to do in terms of our target cost and the cost gap. But let's have a look. We're either going to choose whether the target cost will decrease, increase, or remain the same, and whether the cost gap will increase, decrease. Or we can hopefully narrow it down. The target cost is based on the market price and our markup. So the target cost will stay the same. So it's going to be one of the bottom two. So what will happen to the cost gap if it's now 92%? Well, if we've got a slower learning rate, that is the time per unit is coming down less rapidly, that means the cost will be higher. So that's going to increase our cost gap than if we compare to a 90% learning rate. And then finally, for section B, which of the following statements about a market skimming price strategy for webcam are true? We need to look at all four and work out which combination is correct. First option, it attempts to exploit a market that's relatively insensitive to price changes. This is true of a market skimming strategy, so we can eliminate the bottom one. To discourage new entrants to the market. Market skimming is charging a high price initially, with an expectation we'll decrease that over time. A high-priced product encourages new entrants to the market. So 2 isn't correct. So now we know the answer is this, but let's just check. Where products have a short life cycle, that's true of skimming because what we want to do is get back the costs of bringing that product to market as quickly as possible. And for significant economies of scale, that's a market penetration pricing strategy, not a skimming. The correct answer 1 and 3. That's the end of these 3 section B questions. Thanks for listening.